Hello everyone, this is Maushami. Today I am here with some numerical problems on work, energy and power. So the first question, this question has statement 1 and statement 2. Of the 4 choices given after the statements, choose the one that best describes the two statements. The first statement, a point particle of mass little m moving with speed v collides with stationary point particle of mass capital M. If the maximum energy loss possible is given as F of half mv square, then F is equal to little m by capital M plus small m. Statement 2, maximum energy loss occurs when the particles get stuck together as a result of collision. So now let's explore the two cases, but before that let's understand the problem. We have a point particle of mass little m moving with a speed v. Now this collides with a stationary particle of mass capital M. So what are the possible cases that will arise here? First, let us look at the masses of the two bodies or the particle system before and after collision. So before collision, the mass is little m because the second particle is at rest, and after collision the mass will be equal to little m plus capital M because the two particles, we assume that they get stuck together as a result of collision. Now, what will be the energies before and after collision? Let's look at the energy before collision. We have the energy as half little m v square, and the energy after collision will be equal to half, and then we have to take the mass, that is the mass of the particle system, that is little m plus capital M. Let us try to write the energies in terms of momentum, as we are not sure about the velocity of the particle system after collision. So before collision, whatever is the energy, since they are suggesting in the question that we have an energy loss, so we get a hint in this regard that before collision the net energy is greater than that which exists after collision. So the energy loss will be equal to the initial energy minus the final energy. So the initial energy in terms of momentum may be written as p square by 2 times little m minus the final energy, which is p square by 2 times little m plus capital M. So let's break this up and try to bring it in form. We may write this as p square by 2m, then the first term we have it as 1, and for the second term we may write it as m by small m plus capital M. So if we break up the term that is within the brackets, we get it as the denominator will be little m plus capital M and the numerator will be capital M only. So we may write p square by twice m. This is the initial energy. So in terms of mass and velocity, we may write the first term as this is half little m v square, and inside the bracket we have it as capital M by small m plus capital M. So if we can look at the statements, we see that the first statement is not correct, while the second statement is correct. So we go for option D, that is statement 1 is false and statement 2 is correct. Let's move forward to the next problem. The second question in fact, when a rubber band is stretched by a distance x, it exerts a restoring force of magnitude S equals ax plus bx square, where a and b are constants. The work done in stretching the unstretched rubber band by L is given as. So we have a rubber band that is stretched through a distance x. As a result, the rubber band will offer a restoring force. The magnitude of the restoring force is given as F equals ax plus bx square, where a and b are constants. We are to find out the work done in stretching the rubber band through a distance capital L. So we know here, in case of the rubber band, that is, we have the case of a rubber band means we are to compare this with the case of a spring. So the work done in stretching the rubber band, this is nothing but we have to find that out, we need to recall that the change in potential energy of the system is which is corresponding to a conservative force that is given as F equals ax plus bx square. So let's utilize that fact and find out the work done. So we write this as change in potential energy of the system corresponding to a conservative internal force is the change in potential energy. Maybe potential energy is represented by the letter capital U, and so the change in energy is UF, that is final potential energy minus the initial potential energy. This is nothing but equal to the work done. So this is equal to minus W, as we are talking of the restoring force, and here we have minus initial to final F dot dr. Now we have the value of F here, so the work done in stretching rubber band by L is, we need to find out the magnitude. We shall go for the magnitude only, we shall ignore the sign, and this is equal to nothing but magnitude of F dx. The distance r is nothing but assumed to be x as per question. So we have this. This is what we need. Let's work out the integration part now. We have this as integration. We know the value of f. F is given as ax plus bx square. We need to integrate this, and the limits are from 0 to capital L. So let's integrate this. We'll put in the limits later on. We have integration ax dx. So that's ax square by 2 plus, for the second term we have bx square dx. So it's bx cube by 3. In both of these cases, we have used the formula integration x to the power n dx is equal to x to the power n plus 1 by n plus 1. Now let's put in the limits. We have this as, whenever we put the value of x as 0, the lower limit, we'll see that both the terms will amount to 0. So what we need to do is only put the upper limit. So we have that as a l square by 2 plus b l cube by 3. So we can see that the third option, option C, is the correct option. Now the next problem. A bob of mass little m attached to an inextensible string of length L is suspended from a vertical support. The bob rotates in a horizontal circle with an angular speed omega radian per second about the vertical support. Now, about the point of suspension, which of the following options will hold good? So let us try to visualize the entire problem with diagrams. So there is a fixed support, a vertical support in fact, let's name that as O. We have a pendulum hanging from this particular point O, the pendulum bob, and the bob of mass m, it is attached to an inextensible string. The length of the string is little l and the bob rotates in a horizontal circle. So this is the horizontal circle in which the bob rotates. Let's have the mass of the bob as m. The length of the string here is little l. Now, the angular velocity is omega. So we may see that the velocity v will be resolved into two rectangular components, the radial component and the tangential component. So let's have a look at the components in the diagram. We have the radial component of the velocity here as v radian and the tangential component as v tan. So this basically is the velocity vector v. So this is the thing that we have. Now due to the radial component of the velocity, we have the tangential component of the angular momentum coming up. So let's draw that as well, showing the momentum, the angular momentum in fact. So this is the diagram that we have. We have L radial and this is the tangential component L tan, and this is the angular momentum L, bob of mass m, length of the string L. So this is what we have. Now if we try to understand the direction of the angular momentum, so this is exactly what we are having. Think. This in fact, you can see the direction from here. Trying to plot this, we'll have this in fact. These are the directions of the angular momentum. So you can see very well that the angle made is a right angle and the magnitude here is nothing but m l v. So this is in fact a constant. So we'll go here with option C as the correct one. So let us just jot down the points that we have. V can be resolved into two rectangular components. V radial and V tangential. Now due to V radial, L will be tangential and due to V tangential, L is radial. So the net angular momentum has a constant magnitude which is equal to mvl, while its direction will keep changing as shown in the figure. So now proceeding to the